So good morning everyone, and I would like to thank the organizers for giving me this opportunity to present my research work. So as this title suggests, to branch or not branch, how the plants take this decision through cues from the phytohormone auxin, ROS and water level. So by branching, what we mean is this integrated process of lateral root development. It is a unique post-embryonic developmental process which is regulated by the phytohormone auxin, because auxin acts as the key integrator of both the endogenous as well as the exogenous signals, and through some defined stages the plant forms a lateral root. Now the distinction from a primary root and the lateral root is that the primary root is growing vertically while the lateral root is growing radiovertically. So it provides the plant a nice opportunity to scan its surrounding environment. And this is controlled by the phytohormone auxin. So if we think about auxin, how does the auxin signaling mechanism works? So basically the auxin signaling mechanism is, I would like to call it, is a de-repression module, where in the off state where there is less auxin, the auxin responsive genes are bound by a specialized transcription group of specialized transcription factors known as ARPs, or the auxin response factors. These ARPs bind to the AUXI site, and these ARPs in turn can interact through a common domain with the AUXIAs. The AUXIAs, on the other hand, through another domain known as the ER motif, can interact with this topless. And topless is a chromatin-dependent transcriptional co-repressor. As a result of the recruitment of topless to a particular locus, therefore, the chromatin is compacted, and therefore the auxin response genes are in a repressed state when there is less auxin or threshold levels of auxin. However, as soon as there is a burst of the auxin, or there is an auxin maxima, and we have more auxin, auxin triggers the degradation of this AUXIAs through the proteasomal pathway and the auxin co-receptor TIR1. As a result, now these ARPs are free, and now they can activate the transcription of their target genes. So basically there are two phases: basal auxin signaling mechanism involving ARF plus the AUXIA, then there is repression, and ARF minus AUXIA, and the ARFs are free to activate the transcription of their targets. So essentially it's a de-repression module. Now the interesting fact is, in Arabidopsis there are 29 AUXIAs and about 30 ARFs, and so they can make multiple combinations. And when we consider a combination of an ARF and an AUXIA pair, it is referred to as auxin signaling module. To keep it short, when we consider in this complicated diagram, the thing that we need to understand is, like, there are four primary modules that we talked about in the lateral root developmental program, and where my interest lies is in with IA3, SHI2 and ARP7, which constitutes the module 4. It is considered to be as the gatekeeper in the context of lateral root development, because it has the capacity to influence in a tissue-specific manner both lateral root initiation as well as lateral root emergence. Now, as we talked about the how the plants take decisions to branch or not branch, and how the environment influences, well, this is one of the examples of how the environment is influencing. Few years back, we had a paper from our group where we found out the mechanism by which plants have this tendency to form lateral roots towards water. If we consider a soil environment, it's a heterogeneous distribution of water, and plants would preferably therefore try to form their lateral roots towards the water side, because that is the source, that is the likely source of nutrients. So what we found out is, like, the transcription factor ARP7 is stimulated, and the stimulation of ARP7 then facilitates the recruitment of IA3 through a particular motif within IA3 by which it can interact with the SUMO. This motif is known as SIM motif, or the SUMO interaction motif. When this happens on the drier side, because there is IA3, there is repression, and therefore there is no lateral root formation on the dry side. However, on the wet side, ARP7 is not stimulated, and therefore IA3 is not recruited, and therefore there is no repression, and therefore ARP7 can activate the transcription of the target genes, leading to lateral root development. The question is then, how is ARF7 stimulated and how is it destimulated? In other words, how are these two different states achieved? The answer lies in the way how SUMO is conjugated and deconjugated, or the stimulation machinery, where certain components like the SUMO ligases conjugate SUMO onto their targets. At the same time, we have certain proteases, which are SUMO proteases, that cleave SUMO off the targets. So this becomes a cyclical process and makes it dynamic. Now the interesting fact is that these SUMO proteases are cysteine proteases. That is, they harbor cysteine at the active site. So if you want to inactivate these proteases, you just use chemicals that can inactivate the cysteine residues, which we use here is NU, or enethylmelanin. So when you are doing an experiment where you want your target protein to be hyperstimulated, you will try to inactivate the SUMO protease by using this chemical. So this experiment was done in the presence of DDT, and when I joined Ari's group, I tried to repeat this by changing the buffer compositions, and I added NEM in the buffer. So what happened was, just like the previous finding, we did find out that when we have a non-stimulatable version of ARF7 and a SIM mutant of IA3, the interaction is completely gone, and the interaction also decreases when you have either a non-stimulatable version or a SIM mutant version of IA3. So the trend is similar, but we see some bands at the top. And what is interesting is these bands at the top are forming the same pattern as the ones at the bottom, or the monomeric fraction. Now we just searched the literature and changed again another component into the buffer, and that was diamide. So this component diamide, it just promotes formation of disulfide linkages. So when we use diamide in the buffer, what happened was the same trend was followed, where again in the 4KR mutant of ARF7 and the SIM mutant of IA3, the interaction was completely lost, but all the bands gradually came to the top. So what's happening in this SD state is probably the interaction is there, but so irrespective of the multimeric state, the monomeric form, the multimer, or a mix of both, are interacting in a SUMO-SIM module dependent manner, but probably these higher order multimers in those SDS page gels are redox dependent multimers, because that's the only way this can be explained. So we thought probably different OX-IAs can multimerize through their cysteine disulfide linkages. And then we took certain OX-IAs that represent the different clades of the OX-IAs, and we found out that certain OX-IAs like IA3 and IA19 have a propensity to form higher order multimers, while certain like IA28 have a propensity to form lower order multimers like a dimer, while others like IA30, which obviously has no cysteine residues, so it cannot form redox dependent multimers, while IA14, which despite of having two cysteine residues, do not form multimers. So redox dependent multimerization by the OX-IAs may therefore potentiate for a mechanism by which they can subfunctionalize. And then, so we targeted the OX-IA IA3. So it has total of 7 cysteine residues. Through our biochemical analysis as well as our bioinformatics studies, we found out that there might be certain cysteine residues that are important. So we did a combinatorial mutation, and when we mutated the cysteine residues in our in vitro studies, we found out that the higher order multimers of IA3 are gone, indicating that when we make a combination of these cysteine residues, IA3 loses its tendency to form the higher order multimers. These are in vitro experiments. Then we assessed it in the in vivo system. In transgenic lines, what we found out that the wild type version of IA3 have a very high propensity to form the higher order multimers, and these multimers are robust.
People, you have 2 more minutes.
These multimers are much robust than the cysteine mutant version. Now the OX-IAs have 3 interacting partners, that is the Tier1, topless, and the ARF. So what we found out is that the cysteine mutant can interact with ARF, it can interact with Tier1 but loses its capacity to interact with topless. So what is this impact of this mutation in vivo? So we got a SHI2 knockout mutant line, which was a CRISPR-Cas9 knockout mutant from Dr. Yu Gong's group, And what we saw is that the Shy2 CRISPR has a lateral root phenotype. It forms much more lateral roots because there is no Shy2 to repress the lateral root development. And when we integrate lines that are expressing cysteine mutants as well as the wild type version under the control of the endodermis specific Cas1 promoter and the endogenous promoter, we found out that the cysteine mutant lines cannot revert back the Shy2 CRISPR mutant phenotype. This is well represented in this statistical analysis where you can see while the wild type version can lead to lateral root depression in the Shy2 CRISPR background, the cysteine mutants are failing to do so, both when expressed under the Cas1 promoter as well as the endogenous promoter. So the target genes that are implicated in lateral root development, LBD16 and LBD29, we wanted to assess what is their expression status in the cysteine mutant. Interestingly, what we found that in the cysteine mutant, inherently LBD16 and LBD29, which are key players in the lateral root development process, they are transcriptionally upregulated. So, putting all this information together, this is the mechanism by which we propose where the wild type version of IA3 forms higher order multimers that are recruited to a particular locus through the sumo-sim interaction module, and these higher ordered multimers are well patterned to provide further recruitment of more number of topless molecules. This leads to a more repressed state, whereas the cysteine mutants does form multimers which are less robust and are defective in their ability to recruit topless. As a result, this leads to a basal activated state. So that's it, and I would like to thank everyone who has been involved in this long study, and thank you. Any question for Dipan?
Have you tried manipulating redox in vivo to see whether
Yes, we have. So those experiments are ongoing. So we have tried manipulating the redox in vivo with glutathione treatment, and we have seen that just like the status of 2.5 millimolar DDT treatment, where the higher order falls off, in the wild type that happens when we do it with the GSH treatment.
Oxidized glutathione or reduced or both?
Reduced glutathione.
Reduced glutathione to make a reducing environment.
Yeah, and also we also tried it with the DPI, but because DPI allows endogenous reducing environment, so that experiment is ongoing. It was very difficult to get the DPI.
Thank you.